我这比这个，你看他这次作业了，又出去了。
对啊，
一周一次太多了。啊？难道你们之前不是吗？我上学期做的作业就做完中国，每天做作业就是熬时间，你知道吗？你中国队咋地了？
那还有啥看？
没医药，中国队没医药。
没鸡巴。
因为中国队亚洲杯咋地了？
能少出2个就不错了。
上1对2去。你俩这控制力不错。
对，抱歉，哎，那个我一会儿要去那个南宫 Center， 那个你一会儿帮我看一下，万一大的没来，你帮我把它关了收起来。
他们OK 怎么关？
关就是那个点一下这红的，现在已经是在录着呢。
就按一下这个是吧？
按一下这个，然后把 power 关了，或者直接拔电源就行，没关系。
OK 就好了，然后把它烧起来放那儿。
对，然后不收起来，你先拿你们实验室去，我回来拿。
好，行。
行，万一大的没出现，那怎么办？
是11点的课的。
是11点的课呀。
他没出现意味着啥？
一会儿我来讲。
这话也没有多少。
没事，听不懂。
1、2队控制力100%。
啥？1、2队控制力100%。
2分钟1、2队控制力100%。
好菜。是中国队开的球。
没有直播，看直播。我猜没有直播。
你赌多长时间中国队会进1个球
？15分钟。
这球气了。
哎，没看。哎我靠！那差不多。
是。
So there's a new homework out. Should be much simpler, I think. Just 2 problems. Review of wonder.
Hey, what are you doing?
This one.
Taking it again. No. So that's homework 2. Homework 1 is due today. So you can hand it in if you have not finished it. You want to work on it. You can put it in my mailbox or hand it in to me later today. Okay, so in the last class, we we transformed the Hamiltonian of a system that is interacting with an electromagnetic field, an atom, 2-level atom interacting with an electromagnetic field. And we used 2 transformations. One is one transformation, which is we went to the rotating frame. You remember, right? So that we had 2 more slowly burns. This one is just direct, and then C2 tilde of t we wrote as C2 of t times e to the minus and nu t. This was the rotating frame. That was a transformation. And then in that transformation, we derived that we used then the RWA, the rotating wave approximation, which is valid, which effectively leads to neglect of terms that are oscillating as e to the 2I nu t, or I times, or twice the frequency of the electromagnetic field. And this is valid when one field is near resonance. That is, delta, the detuning, is far, far lesser than the frequency of the field. And B, we also assume that omega, the Rabi frequency, is far, far lesser than nu. So effectively, nu, the frequency of the atom, of the electromagnetic field, is much greater than the detuning, and is also much greater than the Rabi frequency. There's also another subtle approximation, which is that the change in omega, or the change in the magnetic field. So if you have some time-dependent electromagnetic field E of t, dE over dt also must be much smaller in some units compared to this frequency mu. Okay. All right. So, and that all came, if you recall, when I integrated the equation, the second equation of motion, we saw that there were terms that we could neglect if we are sort of looking at the integrals. We could like neglect those second order terms if this approximation is true. And then there was another term which was the counter rotating term, which went as 1 over 2 times the frequency. And since the frequency is large, then 1 over that denominator is very large, which means that that term, which is the counter rotating term, will be very small. Okay, so with all that, and omega we define as a Rabi frequency 2 times mu to 1 dot E naught over H1. Okay, and with that we got this equation of motion. And so explicitly the Rabi frequency omega is allowed to be a function of time. So for example, a pulse of light or microwave or whatever it is. Okay, so the first and solution that we're going to consider is resonant excitation. Which is delta equal to 0 and omega is constant. Or rather you can think of it, omega as a step function. For time t lesser than 0, omega is 0. At time t equal to 0, it turns on and remains constant for some time t. Okay? So this is the condition that we are considering. So we immediately can solve these. So obviously these equations of motion look very simple. Just C1 tilde dot is equal to I omega star times C2. C2 tilde dot is I omega C2t. So then that's easy to solve. Take the derivative of the first equation, d over dt, that will become I omega star over 2 C2 tilde dot now, right? We took the derivative. That's the only time dependent term, which then we can substitute for that from this guy, and that gives us the straightforward solution. So C1 double dot is related to C1 itself through this frequency omega squared over 4. So therefore the solutions are just cosine and sine, and if we impose initial conditions C1 0 equals 1, so initially if we assume that initially the atom is in the ground state and there is no probability to be in the excited state, then C1 tilde of t is just cosine of omega over 2 times t. Okay. And C2 tilde now of t, because it varies as omega times C2 tilde or C1 tilde, I'm sorry. C2 tilde, then we will have the solution I times omega divided by magnitude of omega sine of omega t over 2. Okay. So this second solution ensures that C2 tilde dot is I omega divided by 2 times C1 tilde, right? So that's basically what this is ensuring, this factor here. This factor ensures that this equation is satisfied. Okay? And we can also see something interesting, which is that the phase of omega, remember omega, which is defined in terms of the optical field. The optical field has both an amplitude and a phase. Remember, when we introduced classical optics, I'm sure you all know this, but I'm just reminding you, when we introduced classical optics, we talked about the fact that the optical field has both an amplitude and a phase. And so we can see that the phase of a optical, of an atom, right, the phase of the superposition state of an atom, C1 of t times 1 plus C2 of t times 2, right, that's going to be the state vector of the atom. That state vector of the atom is going to have a superposition that is tied to this phase, right? Because omega divided by its amplitude, right, that cancels out, or the absolute value, the amplitudes will cancel out for the electromagnetic field, right? Because it's just mu dot E naught, that amplitude E naught will cancel out when you divide by the absolute value. So what will be left then is purely the phase of the electromagnetic field, right? So that's why you need, as we will see, when we discuss a little bit more about things like dephasing and decoherence, and also things like Markov approximation, etc. When we do that stuff a little later in the class, you see now that the phase of the electromagnetic field that you use to drive a two-level atom is very critical, because it affects the superposition state. Okay, the superposition of the up and the ground and excited state is tied to the phase of your electromagnetic field. Okay, and this is how by altering the phase of the electromagnetic field, you can make the superposition state change, which is a key component of quantum information processing. Okay, because you've got to be able to, in quantum information processing, create every kind of superposition state of the two-level atom. And that is influenced by this equation. We can do that by just simply altering the phase of the electromagnetic field. Is this clear? It's an important physics point, right? So I want to make sure that we want to understand it. And it also means that if you have an electromagnetic field with a phase that fluctuates, so it's not very fixed. For example, you have a laser, but it's a bad laser. For example, diode lasers are known to mode hop between many different frequencies. Okay? If you took a diode laser and tried to address a two-level atom and drive Rabi oscillations, which is obvious hopefully from here, right? These are Rabi oscillations, right? Clearly. The amplitude, sorry, I should have said that. I jumped over that. So the amplitude of the probabilities, right, or the probability to be in state 1 and in state 2, right, the probability to be in state 1 is clearly C1 of t squared, right? Well, it's really C1 of t, but then C1 of t is the same as C1 tilde of t. So it's just, I can put the tilde or don't put the tilde, it doesn't matter. It's going to be proportional to cosine squared of omega t divided by 2. So you see that this is going to oscillate, right? It's going to go at the Rabi frequency, right? So, alright, so I'm just pointing this out. Sorry, so to back up, then the Rabi oscillations you will just not see because the phase of the oscillation will vary so much that it will start to jitter between cosine and sine all the time, and therefore you will wash out this superposition or this Rabi oscillation. So you need to have very carefully controlled conditions to observe things like Rabi oscillations and so on. Okay? You need a good qubit, you need a good laser, etc. to observe these kind of quantum coherent effects. Okay. So in fact, you will show this in the next homework, that for this delta equal to 0 resonant excitation, and if I explicitly now put in omega of t equals a of t times e to the I phi, okay, so we have a real time varying amplitude and a phase phi, okay, right? So you have this, what would be a typical example in a real experiment, for example, will be something like this, right? So this is now, I'm changing the condition, right? Omega was constant in this expression, and now it's not constant. Now it's actually changing in time, okay? Then you can show that it still obeys these equations. I'm not demonstrating it here, but you will show that by solving these equations of motion. So this guy here, which is the pulse area, right? I mean, this could be 0 or minus infinity, doesn't matter. It just depends on when you turned on the system. Okay. So either way, if this shows you that in fact, as I just, and again you can clearly see now the phase of the microwave of the optical or microwave pulse is going to matter in the superposition state. And as I already wrote down here, the probability to be in the state 1 is this cosine squared omega t over 2, which by trigonometric identity is just half times 1 plus cosine omega t. Okay? And so you can see that the probability to be, say, in the state 1 now will oscillate around the average value half, right? And then it can either go to 1 or 0 depending on the sign of cosine omega t, right? So when omega t equals pi, then cosine of pi is minus 1, and the probability to be in the state 1 is 0. Remember, initially started with the probability to be 100% in state 1. And now after, when omega times t is a pi, equal to pi, that probability will go to 0. So this is called a pi pulse, right? Because you have taken the system which was initially in the ground state, applied an optical field, and made it 100% go into the excited state. Okay? Okay. So that was the that is one solution. Our next solution is for is this clear to everyone? So this is, of course, I haven't shown, but you will show this result in the homework. It's not very difficult. If you look at that, I give you a hint in the homework how to solve this problem. Okay? And this is the exact solution. Okay, so that's cool, right? You've just written down the solution to any two-level atom driven by some time-dependent optical field is done. Okay? So now I want to move on to the next case. Earlier I took delta equal to 0, omega equal to constant. Now I'm going to put in delta. Okay? So I'm going delta is not equal to 0, but I'll still keep omega as constant. Okay? So now I'm taking case 2, delta not equal to 0, and E naught of t, the amplitude of the electromagnetic field, I'm going to treat it as constant. Okay. So again, we can solve for this system. We can go back to the original equations of motion and solve it. Right? That would be the straightforward thing to do. But instead, I'm going to introduce a new technique. Okay. And I'm going to introduce the idea of an effective Hamiltonian. This is also very helpful for understanding the physics and getting intuition about the physics of this system. Okay, so this is the technique we are going to use, which is an effective Hamiltonian. What I claim is that if I look at these equations of motion here, for C1 tilde of t and C2 tilde of t, it looks, and remember this is all in the rotating frame, that is in the rotating frame, and in the RWA. Okay, so these are the two assumptions, approximations, whatever that I've assumed, and with that I have written down a set of equations of motion for the two-level atom. Okay. What I'm saying is now I can think of this set of equations as coming from some effective Hamiltonian, right? Because the Schrodinger equation, basically the evolution of the state ket is determined by a Hamiltonian. And now what I've done is after transforming to the rotating frame and applying this transformation or this rotating wave approximation, I have achieved two new sets of equations for the state ket. C1 of t and C2 of t are the amplitudes of the state ket. And therefore I can think that there's a new Hamiltonian, which I will call the Hamiltonian in the rotating wave approximation, HRWA, which I'm defining as equal to this operator. And to be careful, I'll put the tildes over here because that is the fact that I've transformed to the rotating frame. Okay? So this is the new Hamiltonian of the system in this rotating frame and in the rotating wave approximation. Or you can say that in the 1 and 2 bases, the Hamiltonian in the rotating wave approximation is given by you can convince yourself of this by simply putting it back into the Schrodinger equation, right? Which is that IH bar d over dt of psi must be equal to h of psi, and now of course the psi, if you like, is in the psi tilde in this new rotating frame. Okay, so psi tilde is equal to C1 tilde okay. So if I put back this rotating wave approximation, this Hamiltonian in the rotating wave approximation and the rotating frame back into that, I guess it's all in the rotating frame. That's the tilde is what it's trying to say. Okay. So this Hamiltonian is clearly diagonalizable, right? So we can write down immediately the eigenstates and the eigenvalues. I won't bother going to the procedure, you must have seen this many different times. So find the eigenstates and the eigenvalues. The eigenstates are denoted by the energy, epsilon plus minus is simply minus h bar delta over 2 plus or minus plus, that's because of the sign change over here, h bar over 2 square root of omega squared plus delta squared. Okay? And these eigenstates, which I'm writing down here for completeness, they can be expressed in many different ways, but I'll write them out fully, but you can also express them, for example, in terms of like a mixing angle and so on, which you can also find in many books. Okay? Here I'll just write them out in terms of sort of the actual values of the omega and delta. And if I've dropped the tilde somewhere, please know that it should be there. I might drop it at times, just because it becomes hard to keep doing that. Okay. So these states are called the dress states of the system. Okay. So these are the so-called dress states. You can see why, because essentially that in this approach we have made the system, which I'll draw in just a bit, but maybe it'll be easier for this one. Okay, so let's go back to our original problem, right? The original problem was we had a two-level atom which is being addressed by some field with some Rabi frequency omega and some detuning delta, right? This was the original system, okay? What we have shown is that this is equivalent to a system which is now consisting of these two states, phi plus and phi minus. So phi plus is lower in energy according to, depends on the detuning. I'll come to that in just a second. But anyway, so phi plus and phi minus, which is now split apart by the difference of these two energies, epsilon plus and epsilon minus. Okay? So, and now let's look at some limits of these situations. Okay? So on resonance, when delta equal to 0, so we have taken delta not equal to 0, and we solve the system. So clearly, we can make the approximation now exact resonance. Okay, so on resonance, when delta equal to 0, then epsilon plus minus is simply going to be the Rabi frequency. Right? So the splitting between these two states, when you are exactly on resonance, this is going to be just the Rabi frequency omega. Right? You see that? Right? That is going to be the exact frequency splitting between them when you are exactly on resonance. Okay? And the states phi plus and phi minus is going to be the completely superposition state of 1 plus or minus 2. So that's nice, gives a nice physical picture of what's going on. When you're exactly on resonance, you can also see that when you're exactly on resonance, the diagonal term disappears and you're left with just the off diagonal term. So clearly the eigenvalues of the system are just those two values, omega, right? Plus or minus, when you find out the eigenvalues. So that's the simplest sort of solution. But now we can look at what happens when we are not quite on resonance. In fact, let's go to the other limit. We're going to be far detuned. So now delta is the biggest thing in the problem. Yeah.
Sorry, like here I'm a little confused. So you see, like when you drive no detuning, like on resonance,
Yeah.
the phi plus minus equal to 1 plus minus 2. But like, does that mean the state will oscillate between phi minus and phi plus? Is that what you mean in this case?
No. All I've said here now is, sorry, we just erased it, but basically we are looking at, now you want to know what's the evolution of the system.
Yes.
That depends on the initial condition, how you started, right? So imagine that you initially started in say state 1. Again, just like before.
Oh, so
Right? State 1 is now a superposition of phi plus and phi minus. Right?
I see.
So it's no longer an eigenstate of the new Hamiltonian,
So this eigenstate is just the basis of the
new Hamiltonian.
I see.
Exactly. And because it's a superposition of these two, it will evolve in time. And that's equivalent to the Rabi oscillations, basically. this. So now I want to go to far off resonance. So this is another limit, or well, we are in the same picture of the rest states, but now I'm considering the far off resonance case. Delta is far, far greater than omega. Okay. Now what we can do is, since delta is much bigger than omega, we can Taylor expand the eigen energies and the eigenstates. Right? We can take delta out of that square root and find the expressions in terms of omega over delta. Okay? So Taylor expand. We also have to be careful about the sign of delta. Okay? Because that's going to matter. So first let us take what we call blue detuning. Right? Delta, remember delta is nu minus omega. So blue detuning means that nu is much greater than omega on the positive side. Okay? Nu is much more higher, let's say, higher frequency compared to omega. Okay. So if you like, I'll draw the picture here. Here is 1 and 2, and here is my optical field, which I do with this double arrow just to be a little bit. So this is nu, this is omega, right? So nu is much greater than omega. Okay, if I Taylor expand for this for delta, so modulus of delta is much greater than modulus of omega, and delta is greater than 0, which means nu is greater than omega. Okay. Then the energies epsilon plus are approximately h bar times minus delta minus omega squared over 4 delta. You'll see this omega squared over 4 delta showing up all over the place, so it's good to sort of keep it in mind. And the states, phi plus, will be approximately omega squared over 2 delta times 1 minus 2. And phi minus will be approximately 1 plus omega over 2 delta times 2. This kind of intuitively should make sense to you, right? Because when you have a field that is very, very far resonant or far off from any resonant state, then it doesn't affect the original eigenstates that much, right? As you can see, in front of each of these superpositions is the term omega over delta. Okay? So unless omega is very large and delta is going to be the largest term, this superposition is going to be very small. So when we move from this to the new basis, we don't change the state that much. The state remains almost close to its original state. Okay? So the state 2, for example, has moved to a new state which is almost similar to the old one. Okay? Right? And that is actually the phi plus state over here. Okay? And the energy of this phi plus state, if you look at it, right, is simply minus h bar delta minus this omega squared over 4 delta. Okay? This is another thing to think about, which I should also have mentioned right here. If you go back and look at the original Hamiltonian for the system, right, in the rotating frame and in the RWA, initially we started with the two states. The energy between these two states was omega, right? So this is, let's go back to the original Hamiltonian. So before I applied any electromagnetic field to the system, the Hamiltonian of the system was just simply h bar omega to 2, right? Because remember we took the 0 of energy as the one state. Then we applied this omega delta, which is this, this optical field which has a detuning delta and some frequency. Now we move to a new system, H, which goes as minus H bar delta to 2 plus some off diagonal terms, H bar omega over 2, and you had now 2, 1 and 1, 2, right? Whatever, plus conjugate. Okay? Right? This was the new Hamiltonian. So if I think about what this new Hamiltonian represents, it looks like the state 1 and the state 2 has moved down in energy, or has moved up, whichever way you want to think about it. The state 1 has moved up. So now the two states, 1 and 2, are only separated by delta. In the rotating frame and the rotating wave approximation, they are separated by this delta of energy, and there is a term, omega, that couples them. Okay? Forget it. So this is the physical picture for that Hamiltonian equation that I had written earlier. Right? Everyone clear on this? This is a good physical picture to keep in mind. As soon as you turn on the optical field, then the state of the system now looks like the state 1 and the state 2 are now separated by an energy which is equal to the detuning, and there are oscillations, Rabi oscillations, or whatever you want to call it, a coupling term, a perturbation that connects 1 and 2. Okay? This would be the picture when delta is very small, right, which is near resonance. This is the kind of thing we've been thinking about earlier, right? Now I'm taking the case where delta is far off resonance, which is over here. Okay? So now instead of 2 and 1 moving very close to each other, they still are far apart because delta is still very large. Okay? State 2 moves down in energy a little bit. State 1 moves up in energy a little bit. Okay? That's, as you can see from here, state is epsilon minus, which is the energy of state phi minus, and phi minus is nearly state 1, except for a small admixture of state 2. Okay? So this is phi minus, this is phi plus. And the shift in the energy is the same for both the states, which is this term omega squared over 4 delta. So this guy, this splitting here, or this shift, is omega squared over 4 delta. And similarly, this shift over here is omega squared over 4 delta. And now the separation between these is still the delta. Right? As you can see there. Is that clear to everyone? I guess in this system, if delta is positive, then 2 goes below 1. Right? Because of the minus sign in the Hamiltonian. But that's, you can take care of minus signs. I always get those signs wrong, so be careful about that. Alright. This splitting or this movement of the state by this term omega squared over 4 delta, this is called the AC start shift.
I'm sorry.
Yeah.
So sorry.
Yeah, no, this is good. This is important and you have to stop me.
So now in the case of the drive frequency is bigger than the resonant frequency.
You mean omega is very large?
I mean no, I mean now what if like delta is like it's bigger than omega? What will happen? Like before.
No, remember we cannot have delta bigger than nu. Remember in the RWA, wait, what is your question? Is the drive frequency is small compared to the detuning? Is that what you're saying? Or delta is small compared to omega? Is that what you're asking?
So no, I mean I mean, delta is the frequency difference between the drive frequency and the resonant frequency.
Exactly.
Right.
Correct.
So like before, like when you put on the drive here, the energy difference is omega, right?
The energy difference between the atomic states is omega.
Yeah.
Correct.
What if like my drive frequency is like too far away from the resonance? It will become like 2 omega, 3 omega. Then the delta will become more large, even larger than omega.
Yes, but we can't have it because remember that we have always said that for the rotating wave approximation to be valid, that nu needs to be the largest frequency in the problem, and it needs to be bigger than delta or omega, or delta or capital omega. There's a small omega which is the atomic frequency. But
so even in this case, like the far
even though it's far detuned, it's not so far detuned that it becomes much greater than. It's still everything has to live within the RWA. Okay, that's already assumed. Okay, I couldn't get this Hamiltonian if I didn't have the RWA, right? Nu has to be the biggest frequency in the problem. The drive frequency has to be the biggest frequency in the problem. Is that okay? I'm just saying, for example, that you may be far detuned relative to the Rabi frequency, and this could easily be done. For example, delta can be small if your Rabi frequency is extremely tiny, right?
Yeah.
So this is actually a good thing to think about as a sort of like an analogy to perturbation theory, right? So when you think about like when you do time-dependent perturbation theory in your quantum mechanics textbook or in your graduate quantum, usually you say, well, I can assume that the perturbation is small. What we really mean by that is that the amplitude of the electromagnetic field is small, right? So omega can be very small, for example. If you turn down some drive frequency, but it's a very weak drive frequency, then this condition is easily satisfied. And you're far detuned relative to that, right? That's what I mean by this. Right. So there is this. These are the exact solutions, but as I said, they're not very helpful a lot of times. Because I'll show you, that we can think about it in a more graphical representation. Okay. So now that we have done the blue detuned case, that is delta is positive and much greater than the Rabi frequency. Now we can go to the red detuned case. So now delta is lesser than 0, but also still satisfies that mod delta is much greater than omega. And yeah, that's pretty much it. Okay. So still that condition is satisfied. Well, then now you can make the same approximations, and you find that now the sign of these things has flipped. So because delta is negative, this is can be written as minus h bar omega squared by 4 modulus delta, right? Because delta is negative. And similarly, epsilon minus is approximately h bar times delta plus h bar omega squared divided by 4 modulus delta. Okay. So basically I put in delta equals minus the modulus of delta. And then phi plus the state, which originally now goes as minus 1 plus omega by 2 delta times 2, and phi minus goes as approximately omega over 2 delta 1 plus 2. So we see now that sort of because of the detuning, we have essentially shifted which state we identify with phi plus and phi minus. So now phi plus is nearly the state 1 with a small admixture of state 2. Phi minus is nearly the state 2 with a small admixture of state 1. Okay. And so if we look again at the same picture, now we have 1 and 2, and now our drive laser or microwave or whatever is far detuned from state 2, but on the red side. It's red, right? Well, you see now that what it does is it pushes the levels apart. Okay? Which means, and this is now the state plus, this is now the state minus. Whereas earlier, this was the state plus, and this was the state minus. So one interesting thing you can see is that when the atom is, say, in its ground state initially, and you apply a red detuned laser, it shifts the energy of this atom low. Whereas the blue detuned laser shifts the energy of the atom higher. This is the fundamental reason why atoms which are in some internal state will behave differently depending on the detuning of a laser. So when you look into things like the movement of atoms, atom trapping and atom cooling, laser cooling and so on, this is the fundamental sort of reason. This is the effect of the dipole force on the atom, is that when the laser is red detuned, the atom wants to move towards the region of higher intensity of the laser because that lowers its internal energy, right? Whereas when you are in this state, or in this system, when you are in the blue detuned regime, you cause the atom to get repelled from the region of high intensity of the laser. Okay? So this gives rise, this is the fundamental way in which the atom trapping and atom cooling, laser cooling community has used these kinds of effects to great success. For example, in cooling a gas of atoms down to almost zero temperature. Yeah, this I have only told you about conservative forces here, right? Because everything I've written here is conservative, right? In the sense, it's a Hamiltonian description, okay? So this allows you to do things like trap the atoms, move them around with the forces that you can apply by applying a laser to them, but I haven't told you how to cool the atoms. That you have to wait till I cover dissipative interactions, because cooling, of course, requires that I somehow remove energy from the system, okay? And that requires that there be some dissipation, okay? We'll come to that later, okay? But right now, this part is sort of the fundamental unit of all atom trapping sort of experiments, that you need to have this control over the laser and the detuning and so on.
So if we do this, try to cool the thing, we
You can't really cool it. I mean, the kinetic energy, you can't cool it.
Okay, so there will be another mechanism to remove the energy.
Right, right. But what this does is, imagine that you have an atom in its ground state, and the atom, you want it to like sort of, it creates like a potential well, for example, for the atom, okay? And so if the atom is moving slowly, it can come into that potential well and get trapped, okay? Right? But that doesn't take away any more of its sort of distribution of energy. So if you have a distribution of atoms, cooling we really mean is we want to narrow that distribution of energy, the velocity distribution, right? That's really what we mean by cooling. We want to gradually remove the variance in the energy till they all are in the sort of the lowest state of kinetic energy, and then we have cooled the system. No. That's what, because the temperature has changed, right? Because temperature is related to the variance of the distribution, okay? That's what we mean by cooling in the statistical mechanics sense. Yes, it is true that, you made the individual atom's kinetic energy, like it had a kinetic energy and some potential energy outside the laser field, and then as you moved it, then some of that went into the potential energy of the atom and away from the kinetic energy, for example, right? But you didn't change anything about the distribution of the atom's kinetic energies, which is what you really need to do if you want to cool the system to zero temperature, for example. Because nothing in this argument here is dissipative. There's no dissipation in this argument. Okay? But it is a good way to trap atoms, for example. You exert some forces on the atoms.
It's like you create potential.
You create a potential, exactly. Right. And this is like, for example, if you look at all the experiments people are doing in quantum simulation right now, okay, with cold atoms, this is the effect they are using. So once you have a gas of atoms with very cold and it's almost in its ground state, so that they can all be essentially described by the same wave function or something in a Bose-Einstein condensate, if you now turn on some laser, for example, they turn on like 3 sets of lasers, or 2, let's say you have 2 counter-propagating lasers, right? That creates like a standing wave potential, standing wave pattern of the field. And what this is saying is that standing wave pattern, if you are, say, red detuned, if those 2 lasers are red detuned from the atom's transition, right, then that creates like a variation in the internal potential energy for the atom. Because the high intensity regions are lower energy and the low intensity regions are higher potential energy. So this is the way in which they can make those atoms now trap into like potential wells, which are in a periodic pattern. Okay? So that's how the cold atom community is now trying to simulate things like, you know, Hamiltonians of many body systems. They take a gas of atoms and then they apply like 2 counter-propagating waves. Okay? Now these 2 counter-propagating waves are effectively creating a potential, periodic potential energy for the atoms in this state, in this cold atoms. Okay? So that periodic potential now just looks like a standard solid state physics problem. Right? You have a bunch of atoms all in the same wave function, can be described identically by the same wave function, and now you've created like a solid, like a periodic potential. And now you can change things like the interactions between the atoms, also through various tricks that they play with lasers and so on. You can make them interact with each other. So it's given rise to this whole beautiful set of physics, this community of doing many body simulation, many body quantum simulation using cold atoms. Okay? And the fundamental sort of physics is coming from here. Okay, and so, any more questions about this? I guess what you should take away even more than the actual expressions may be sort of these physical pictures, right? That initially you started with the energy states which were like sort of separated by delta in the rotating frame. And then as you apply the electromagnetic field, if it's far detuned, then you're causing some shifts in the energies. Those shifts, even if I wake you up in your sleep, you should be able to tell me the shift is omega squared over delta. Okay? Like that kind of thing. And the mixing will be going as omega over delta, which makes sense from a perturbation theory argument also. Right? When delta is the largest term, the first, perturbation will be first order will mix up omega and delta in that ratio, right? So hopefully this all is making also some physics sense, not just the mathematical equations. Yes, the mathematical equations are nice to have, but then having this physical picture lets you think about problems which are maybe which are more complicated than this, right? So obviously this is a very simple problem in some sense. So now we want to think about more complicated problems. Leave the pictures up there. So now I want to discuss the next thing, which is we can make now a continuous variation going from of detuning versus energies. Again, remember, as you asked me, that question, we cannot have delta be much greater than, say, nu, for example. So delta is large, but it's large compared to omega, right? So you can think of it as, maybe the parameter here that should be written is delta over omega, right? That's kind of the picture that I'm drawing. Okay. So delta can be positive. Let me take away the symbol because this is now positive or negative. Okay. So as we just said, when it is far red detuned, which is on the negative side, okay. Oh, okay. So first, before we apply any thing, we should think about what happens to the bare states, which is the 1 and 2 states. Okay, bare state 1. As I sweep the detuning. Okay, I've kind of dashed it over here. Nothing happens to state 1 because remember in the original Hamiltonian, state 1 was always taken to be having 0 energy. Okay? So as detuning changes, nothing happens to state 1. You can of course make this different, okay? If you decided to set that 0 of the original, so remember again, going back to the original Hamiltonian, state 1 was at 0 energy, state 2 was at energy omega, right? Okay, and then when we applied the, or we went to the rotating frame, right? When we went to the rotating frame now, this guy, well, they switch their energies depending on the detuning, but if you are if you are like say, so it's just minus of delta, right? That's the energy of state 2, okay? So when delta is less than 0, state 2 is at higher energy compared to state 1, okay? So we start here. State 2 is over here, okay? And when we are at the opposite situation, state 2 is now at lower energy compared to state 1, okay? Just from going to the rotating frame, right? And so if omega is very small or something and we don't need to worry about this, we just connect up. Sorry, I have a hard time drawing on this board. Sorry, that didn't look very straight, did it? I was trying to make it very big and then it makes it look ugly. I just now, hopefully now that you understand it, I can just draw a straight line. Okay. Still not very straight, but I hope you get the picture. Is that okay? Reasonably straight. Okay. The drawing is too big for it. Okay, and now, so now we see that when we turn on omega, or make omega slightly larger, so that it's not completely close to 0, then you're going to get a new state, which is the phi minus state, which as we showed earlier, that when you're in the red detuned regime, phi minus is almost equal to state 2, phi plus is almost equal to state 1. Okay? And so, this is phi plus, and we know that the states shifted down in energy and up in energy, like that, like as I showed in that over there, in that drawing, right? State 1 shifted down, state 2 shifted up, okay? And on the other side of the drawing, then the opposite happens. The state over here shifts that way, and the state over here shifts down. So now again we can draw smoothly, except that now we know that it's not going to be a straight line, it's going to be some curved figure or curved expression, which I draw sort of like that. Okay, and this guy is going to be some thing that approaches the original state 1. Okay. So this picture, and then exactly at delta equal to 0, the splitting between them, as we already showed, is just simply h bar omega, which is the minimal splitting that you can have in this situation. Which, if you remember, when delta was 0, then the states 1 and 2 became exactly separated purely by the Rabi frequency omega. Okay. So this is actually a very important figure, again, to keep in mind when we think about things like manipulation of qubit states, for example. Because one nice thing about this is what it does. For example, we have talked about Rabi oscillations, right? And we said, well, if we initially start in state 1 and we turn on at resonant with 0 detuning, if I turn on a optical field, I can make all of the population go from state 1 up to state 2, right? And we said, what are the conditions for that to happen? What does the product omega times t have to be equal to? What is that thing called? When I make the population go all the way from state 0 up to state 1, I gave that a certain kind of, It's called a something pulse. Pi pulse, right? It's a pi pulse because omega times t had to be equal to exactly pi for the Rabi oscillation to be perfect, to go from 0 up to 1. Okay? Or sorry, state 1 up to state 2. And that is very good if you have very fine control over the Rabi frequency and the time of the pulse. Okay? But there are situations where you don't have that fine control, or maybe there are other effects such as decoherence and so on that are going on. This different picture gives us another way to achieve the same kind of effect of going from the state 1 up to the state 2. Okay? This is called adiabatic passage. Okay, and I'll explain why it's called adiabatic in a little bit. But the idea of this is, I start with everything in the state 1, right? And I take my optical field and I start it far off detuned. It's much easier to control frequency sometimes than it is to control the magnitude of the amplitude of the pulse. Okay, carefully. Because remember, for the pi pulse, I had to make omega times t, the time of the pulse, times the Rabi frequency had to be exactly pi to achieve the exact pi pulse. So let's say I start with all of the population initially in state 1 in this system. Okay, right? And now I turn on my drive laser, and it is far detuned, red detuned over here. I gradually sweep the frequency of the laser from minus up to plus, and you can see what's going to happen here, right? Essentially, the system is going to follow this dynamics of this process and end up on the other side, okay, with everything in the state 2. Because it's going to follow this guy here. Phi minus, phi minus, phi minus, and suddenly you see phi minus has become the state 2 over here on this side. Okay? Does that make sense? Right. So I start with everything like that, like that, like that, like that. And then magically, at this point, the two switch over, and I've ended up with all the population in the state 2. Okay? And the reason it has to be adiabatic, I'll explain that in a second, is I don't want it to transition over to this arm over here, because right at this point, when the states are actually, so if I keep following everything adiabatically, remember adiabatically essentially means I'm doing it so slowly that essentially the system remains in its eigenstate, phi minus. It never flips over to the other eigenstate, or it stays in the eigenstate phi plus, never flips over to the eigenstate phi minus. So if I do it slowly, it will always remain close to this state. And the danger point is here, because this is the minimal splitting between the states. At this point, the two states are closest in energy, and I could have a transition going over to the other state. Okay? So that is what I mean by adiabatic. And I'll give you more quantitative details maybe in the next class. But the point of this experiment, or this what is this thing called, is adiabatic passage. I start with the system in the one eigenstate of the Hamiltonian. The eigenstate of the Hamiltonian is that it's in the state phi plus, which is close to the state 1 when we originally started. And by sweeping the frequency slowly, I end up in the state 2, because I never transitioned from this eigenstate to the other eigenstate. Okay? And that's it. That exactly achieves this Rabi pulse, the pi pulse, the same effect as the pi pulse. Of course, there are issues here. For example, what about decoherence? What about other things? And so those are the things we have to look into. Okay? Yes?
So in this experiment, you are actually sweeping the frequency, like increase the frequency slowly.
Correct.
But how do you do it in the real experiment? Like how do you make sure you are not excited to the bypass in the real experiment?
So the idea is that you, essentially the rate of sweep, delta dot, right? Delta dot represents the rate with which I am changing the frequency. Okay? Has to be much smaller, okay, than omega, the Rabi frequency, okay, well, as you will see, it has to be, this doesn't quite make sense, there has to be one more frequency. One second. This is the detuning divided by frequency. I've derived the actual expression in the notes, but I'm just trying to come up with the physical picture right now. Okay, what else is in the system? It's the delta again. So I'm guessing that this must be some combination of omega and delta. Maybe omega squared over delta. Okay, I'll look it up. But basically, I think what is happening is that you have to have that the rate with which you're chirping or changing the frequency of the drive has to be much smaller than the rate at which you make transitions from here to there. Okay, and the rate at which you make those transitions is going to be governed by omega, the Rabi frequency.
So you mean like at every point on this axis, so
Yeah.
there were no Rabi oscillations.
Right.
Anyway.
You don't want the system to flip into the other state, which it will do if, for example, the Rabi frequency is you know, if the rate with which you're changing this is large compared to the Rabi frequency, for example.
Okay.
I will derive the exact expression, but the idea for this can be seen also from like thinking about the rate with which you carry out transitions from one system to the other, right? So the rate with which I carry out the transitions from here to here is going to be governed by one, the rate with which I modify the parameters of the Hamiltonian and the Rabi frequency omega. These two have to be somehow kept in check so that you make sure that you don't transition over there. If you did this instantaneously, clearly there are a lot of frequencies in the problem, meaning there's a large bandwidth in the problem, if you think about it that way. So maybe another way to think about it is like this, like using some kind of like a Heisenberg uncertainty sort of argument, which is that if you hit the system with detuning and then you rapidly sweep the detuning, it's like you're broadening out this eigenstate a lot. Once you broaden this eigenstate out a lot, it has a lot of overlap with the other eigenstate, okay? And that other eigenstate effectively is now the other state, and then you'll go back to the original state one, okay? So I can make all this more quantitative, of course, okay? And I'll do that when I talk about adiabatic theorem and adiabatic passage in the next class, okay? I also want to introduce one more technique which is very important, which is called adiabatic elimination, but I don't want to get into it today because it is a kind of subtle and interesting technique. So maybe in the next class what I'll do is I'll cover adiabatic elimination and adiabatic passage, and that will hopefully answer this question a little bit more quantitative, okay? I'm giving a qualitative sort of idea, but we should be more quantitative, okay? Any other questions? And so, like, I can give you an example of how I use adiabatic passage in my own experiment. So, for example, like we were just discussing, right? Suppose you want to like determine you don't know whether your Rabi pulse, for example, was doing a full Rabi oscillation or whether it was only doing a partial Rabi oscillation. For example, you're doing what's called state tomography, and you want to determine with great fidelity whether you've actually carried out an experiment where you flipped from state 0 up to state 1. Okay? So to do that, if you try to do just a Rabi oscillation, how do you know that your Rabi pulse is perfect? So now you've brought in another source of error. You've brought in the error from making measurements, and you've brought in the error from not knowing your Rabi pulse, whether it is perfectly a pi pulse, right? Because if you want to think about, I already indicated somewhat the block sphere picture to you guys, right? So, but if not, I'll remind you again. You start with everything in the state 1, and then you go up to state 2, right? State 1 and 2 are like the south and north poles of the block sphere, okay? I'll be introducing this again later on, but so now when you do a pi pulse, effectively what you're doing is, and you can see why it's called a pi pulse, you're going along the block sphere from state 1 up to state 2, okay? If you have a perfect pi pulse, you know already that your pi pulse is perfect, then it's okay. Then you can just measure the population or whatever signal that you have for 1 and 2. You have some readout that tells you whether you're in state 1 or state 2, and you know that, okay, you've done a good job for the state fidelity preparation and state tomography and so on. But what if you don't know how good your pi pulse is to begin with? Okay? Because that's something you probably want to calibrate in the system. Then this is what gives you an alternative way or a better way maybe to calibrate your measurement readout. Because we know we can prepare it in the ground state, right? There is some protocol you follow, you prepare it in the ground state. Then you make your readout measurement and that tells you the probability to be in the state 1. And you're pretty sure because you prepared in state 1, your signal is only affected by the measurement fidelity of whether you're in state 1 or not. And I'll define all these things later on more carefully, what I mean by measurement fidelity and all that, but that's not important. And then what I do is I turn on my microwave or optical field, and I slowly vary the detuning of my microwave or optical field from large red detune to large blue detune, okay? And at the end of this process, I'm guaranteed that I will be in the state 2, okay? And there are easily parameters. Once you measure all the parameters of the system, you can easily determine what range of chirping that I can do. Chirping, right? It's chirping because I'm changing the frequency of my drive laser as I go from one end of this to the other. And at the end, I'm guaranteed I'm in state 2. Now I make a measurement readout. So I know I have prepared the system now in the state 2. Okay? So this gives you an independent way to make sure that your measurement readout is not governed by how well you can go from state 1 up to state 2 by the pi pulse. Now you can go and calibrate your pi pulse next. You can say which of the pulses gives me the best measurement similar to this one of going from state 1 up to state 2. So this is how I carried out, and I'll come back to all this when we discuss the quantum information aspect of this class. This is how you would carry out in a real experiment, like measurement of fidelity of the pi pulses and your measurement of your state 1 and state 2 and so on and so forth. Just a, sort of real world or whatever quantum world application of rest of adiabatic passage experiments. Okay, so I'm going to erase all this, and next class we will come back to this and we'll do it more quantitatively. Okay? And I'll also cover adiabatic. Yes. Okay. Yeah. Put my mailbox or just slide it under my door. Put 24 hours. My mailbox is just with the. Yeah, you have to put my name on it, otherwise they won't.
我不知道他们就这个问题什么意思？我理解他是相当于把这个但是他讲的这样，只有引入一些 display。